Hello everyone, and welcome to Earth Archives. Quantum mechanics, a field that sounds both mysterious and filled with science fiction, often brings to mind phenomena that are difficult to understand and may even leave us feeling a bit confused. For example, when we hear the term Schrödinger's cat, many people might immediately picture a cat locked in a box and then ask themselves, what's going on here? How is a cat related to quantum mechanics? In fact, Schrödinger's cat is not a real experiment. To put it plainly, the cat doesn't exist. It is simply a thought experiment. Many phenomena in quantum mechanics defy the physical laws we commonly understand, and this is why some physicists use strange examples to help explain them. Schrödinger's cat is one such example. Of course, such a concept might seem absurd and even hard to believe because it contradicts our intuitive understanding of reality. However, this is precisely the charm of quantum mechanics. It breaks through the familiar laws of physics and takes us into a microscopic world full of miracles and uncertainties. The next time you hear the name Schrödinger's cat, try imagining that cat both alive and dead at the same time and feel the wonder and mystery of the quantum world. Perhaps this is the most captivating aspect of quantum mechanics. It makes our world seem even more incredible. Schrödinger's cat, a cat that's both dead and alive? The story of Schrödinger's cat may sound like something from a science fiction novel, but it's actually a famous thought experiment in quantum mechanics designed to help us understand the strange phenomena of the quantum world. Let's take a quick look at the background and meaning of this story. Imagine a cat locked in a completely sealed box, and inside the box is a radioactive atom. This radioactive atom has a 50% chance of decaying and a 50% chance of not decaying. If the atom decays, it triggers a mechanism that breaks a vial of poison gas, which then kills the cat inside the box. If the atom doesn't decay, the cat remains unharmed and stays alive. The problem arises. Before we open the box, is the cat dead or alive? According to the interpretation of quantum mechanics, the cat is actually in a superposition state, meaning the cat exists in both a dead and alive state simultaneously, until we open the box and observe it. Only when we observe the cat does this superposition collapse, and the cat will either be dead or alive based on the outcome of the decay. This may sound incredibly absurd, as it's something that can't happen in our daily lives. How could a cat be both dead and alive at the same time? However, this is precisely the nature of quantum mechanics. Particles in the quantum world, whether photons or electrons, don't follow the intuitive rules that we're used to with macroscopic objects. In the microscopic world, the state of a particle is often uncertain, and it is only when we make a measurement or observation that these states become fixed. So, Schrödinger's cat isn't meant to tell us that a real cat can simultaneously be dead and alive, but rather to illustrate the concept of superposition in quantum mechanics. In the quantum world, the true state of a system can't be determined before it is observed, which is a major departure from our everyday physical experiences. This is why Schrödinger's cat has become a classic thought experiment in quantum mechanics. It helps to reveal the strange and mind-boggling nature of the microscopic world and shows us that things in quantum mechanics don't operate according to conventional logic. This counterintuitive phenomenon is one of the reasons quantum physics continues to attract scientists and scholars to delve deeper into its mysteries. Why do such strange quantum phenomena occur? To understand the peculiar phenomena of quantum mechanics, we first need to look at its origins. The birth of quantum mechanics wasn't instantaneous, and early scientists didn't initially think it would differ significantly from the macroscopic world we are familiar with. Their thinking was simple. They believed that the rules governing the quantum world should also follow similar principles to those governing macroscopic objects, such as vehicles and airplanes. In their view, whether it was something as large as an airplane or as small as microscopic particles, there should be certain rules to follow. However, as research deepened, scientists gradually realized that the behavior of the quantum world was vastly different from our everyday experiences. In the macroscopic world, we can easily calculate a car's speed, position, and other data. These values are definite, or at least they seem so to us. But in the quantum world, things become much more complicated. According to Heisenberg's uncertainty principle, in the quantum world, a particle's speed and position cannot be measured precisely at the same time. In other words, the more precisely you measure a particle's position, the more uncertain its speed becomes. Conversely, the more precisely you measure its speed, the more vague its position becomes. This phenomenon is almost unimaginable in the macroscopic world, as we typically assume that the speed and position of an object can be determined simultaneously, which seems intuitive to us. This explains why, in the quantum world, the behavior of things cannot be understood using the classical physics principles that apply to objects in our daily lives. It not only challenges our understanding of the world, but also makes us realize that the quantum world does not follow the logic and rules of the macroscopic world. Just like we saw in the Schrödinger's cat thought experiment, many phenomena in quantum mechanics, ranging from observing particles to the measurement results, are filled with uncertainty and ambiguity, which is completely different from the physical laws we are familiar with. Quantum superposition and wave function. In quantum physics, the wave function is an extremely important concept. It represents the probability distribution of a particle in various possible states. Simply put, the wave function tells us where a particle might be and in what manner it might exist, but these states are not definite. Instead, they exist in a state of probability distribution. This is why particles in quantum mechanics do not have specific, definite existence states when we are not observing them. To help understand this concept, imagine you are playing a coin toss game. When you toss the coin, it has a 50% chance of landing heads and a 50% chance of landing tails. Before we observe it, the coin is not in a definite state, but instead it exists in a probability distribution state. In other words, the coin is in a state that could be both heads and tails at the same time, and only when the coin lands and we observe it does it collapse into a definite state, either heads or tails. This situation is very similar to the behavior of quantum particles. In the quantum world, particles are like that coin existing in a superposition state, meaning they can be in multiple possible states at the same time. Only when we observe them do these states collapse into a definite result. Just like when tossing a coin, it is not simply heads or tails before we observe it, but exists in various possible outcomes, and we only know the result when the coin lands. This phenomenon reveals a very peculiar characteristic of quantum mechanics. Observation has a decisive influence on the state of a particle. Before we measure or observe quantum particles, they do not have a definite position or momentum. Instead, they exist in a vague probability state. This is one of the major differences between the quantum world and the macroscopic world we are familiar with. How did Schrödinger arrive at this conclusion? Before proposing the thought experiment of Schrödinger's cat, Schrödinger was already one of the leading figures in the field of quantum mechanics, making significant contributions to the development of quantum theory. However, at that time, quantum mechanics had reached a crucial turning point, especially with the rise of the Copenhagen school, which led Schrödinger to begin questioning these emerging theories. The representatives of the Copenhagen school, such as Heisenberg and Bohr, argued that particles in the quantum world do not exist in a definite state, but instead exist in a superposition state. This means that, before being observed, a particle's properties, such as its position and momentum, are not fixed, but exist in a probabilistic distribution. According to this theory, a particle state will only collapse into a definite state at the moment of observation or measurement. In other words, the observer's actions have a decisive impact on the outcome of the quantum system. However, Schrödinger did not fully accept this viewpoint. He argued that if the theory of quantum mechanics can explain the microscopic world in this way, should not these same rules apply to the macroscopic objects in our everyday lives? He used a highly controversial thought experiment to challenge this theory, which later became a classic in the history of science. The Schrödinger's cat experiment. In this thought experiment, Schrödinger imagined an extreme scenario. A cat is placed inside a sealed box, and inside the box, there is a radioactive atom. This atom has a 50% chance of decaying and a 50% chance of not decaying. If the atom decays, it triggers a mechanism that releases poison gas, killing the cat. If the atom does not decay, the cat remains alive. According to the Copenhagen school's theory, before observation, the cat should exist in a superposition of both dead and alive states. Only when the observer opens the box does the cat's state collapse, determining whether it is dead or alive. Schrödinger proposed this thought experiment precisely to emphasize the absurdity of applying quantum theory to explain the behavior of macroscopic objects, like a cat. He believed that if quantum theory could explain the microscopic world in this way, then macroscopic objects should also follow these rules, which not only defies intuition, but also contradicts our common sense of daily life. Through this experiment, Schrödinger challenged the Copenhagen school, attempting to provoke deeper discussions on the foundations of quantum theory. Challenges and controversies in quantum mechanics. Schrödinger's cat thought experiment certainly sparked significant divisions within the field of quantum mechanics and pushed the development of this domain into more complex debates. One of the central issues in this debate is whether the strange and even absurd phenomena revealed by quantum mechanics are fundamental laws of nature, or whether our understanding is still incomplete and there must be a deeper explanation. On one side, supporters of the Copenhagen school believe that the features of quantum mechanics, such as the superposition and collapse of particles, are fundamental characteristics of the quantum world, inevitable and unavoidable. These scholars argue that the randomness and uncertainty in quantum theory are intrinsic to the microscopic world, and these phenomena are not extensions of our daily experiences, but rather unique aspects of quantum reality. They accept the observer effect in quantum mechanics, and contend that a particle state only collapses into a definite result when measured, considering this a natural part of the quantum world with no need for a more intuitive explanation. On the other side, figures like Schrödinger and Einstein were skeptical of the randomness and uncertainty in quantum mechanics. They argued that, although the behavior of the quantum world appears random, this does not mean it is without underlying order. Einstein, in particular, was famously opposed to the randomness in quantum theory and famously said, "God does not play dice." He believed that the randomness of quantum mechanics was simply a manifestation of laws we had yet to discover. He held that there must be some underlying deterministic laws at play, which we just could not fully understand or uncover yet. Einstein's skepticism towards quantum theory did not mean he rejected the mathematical framework of quantum mechanics, but rather that he challenged its physical interpretation. He believed that the randomness in quantum mechanics represented an incomplete theory that still required a more complete explanation. The fundamental point of contention in this debate lies in whether the quantum world truly involves randomness, or if its apparent randomness is merely due to our inability to fully understand the underlying laws. This is also one of the profound philosophical questions of quantum mechanics. Can we truly understand the fundamental laws of nature, or are there inherent limitations to our own cognition? Many worlds interpretation, the birth of parallel universes. As quantum theory developed further, scientists gradually proposed more and more explanations to understand the peculiarities of the quantum world. One of the most revolutionary interpretations is the many worlds interpretation, or the parallel universe theory, proposed by Hugh Everett in 1957. This theory challenged the traditional Copenhagen interpretation and offered a completely new way of understanding the observer effect and quantum measurement in quantum mechanics. In the traditional Copenhagen interpretation, the state of a quantum particle is in a vague superposition until it is observed, at which point it collapses into a definite result. This is similar to Schrödinger's cat thought experiment. Before we open the box and observe the cat is both alive and dead, and only upon observation does the cat's state become definite. However, Everett's many worlds interpretation presents an entirely different view. He proposed that quantum measurement does not cause the collapse of the wave function, but rather the universe itself splits. In other words, every time we perform a quantum measurement, the world splits into two or more parallel universes, each corresponding to a possible quantum outcome. These parallel universes are independent and do not interfere with or affect each other. Taking Schrödinger's cat as an example, according to the many worlds interpretation, when we open the box to observe the cat, the world splits into two parallel universes. In one universe, the cat is dead. In another universe, the cat is alive. In this way, the cat's fate no longer depends on whether we observe it, but on the outcome of the quantum event. These outcomes cause the universe to split into different worlds, each with a different result. In these parallel universes, the cat's life and death are not mutually exclusive, but exist in their respective parallel worlds. This theory offers an explanation that no longer relies on the concept of wave function collapse to understand quantum measurement outcomes. Each quantum event actually causes the universe to split, allowing every possible outcome to occur in a parallel universe. In this way, the results seen by each observer in each universe are real, though they exist in different universes. The many worlds interpretation not only resolves the Schrödinger's cat paradox, but also provides a completely new way of viewing the universe. According to this theory, the universe we live in is just one of countless parallel universes, with all possibilities being realized in some parallel universe in some form. These universes are independent of each other, unable to perceive or influence one another, but their existence is parallel and equally real. Despite the many worlds interpretation being an attractive theory for many physicists, it remains highly controversial. Since the parallel universes it involves are beyond our direct observation, it is still considered by some to be a philosophical or even science fiction hypothesis. Nevertheless, with the continued development of quantum mechanics, this interpretation still sparks heated discussions and research within the scientific community. Quantum mechanics and our world. The wonder and mystery of quantum mechanics remain one of the most exciting yet perplexing areas of physics to this day. From Schrödinger's cat to the many worlds theory, these revolutionary concepts challenge our fundamental understanding of the reality around us, even redefining the scope of physics and our understanding of the universe. Quantum mechanics tells us that the rules governing the microscopic world are far from what our intuitive common sense can explain. In this world, particles are both waves and particles. States are both definite and fuzzy, creating an experience that is both mysterious and strange. Schrödinger's cat, a seemingly absurd thought experiment, not only shows us the absurdity of the quantum world, but also prompts profound reflection on the observer effect and the measurement problem in quantum mechanics. Meanwhile, the many worlds theory boldly challenges conventional ideas, proposing that every quantum event results in the creation of a parallel universe, where all possibilities coexist. These theories undoubtedly lead us to reconsider the nature of reality and our own place in the universe. Although these quantum concepts may confuse many, they have also sparked the exploration enthusiasm of countless scientists. The strange properties of quantum mechanics are not only pushing the boundaries of physics, but also paving the way for infinite possibilities in future technological developments. The advent of cutting-edge technologies like quantum computing, quantum communication, and quantum encryption is built on the foundations of quantum mechanics. These may revolutionize our understanding of information processing, transmission, and security, guiding us into a new technological era. Quantum mechanics, a field that seems complex and mysterious, remains a challenge for us today. It has not only transformed our fundamental understanding of the physical world, but also opened the door to the exploration of emerging technologies, from quantum computing to quantum communication, all deeply influenced by its profound principles. Perhaps in the near future, as we break through our current understanding, we will truly unlock the gates of this mysterious world and reveal deeper laws that govern the universe's operations. When that day arrives, we may find that the truth of the world is far more wondrous and complex than we currently imagine. The theories of quantum mechanics, whether Schrödinger's cat or the many worlds theory, challenge our basic understanding of reality, pushing our thinking toward grander and deeper directions. If you still have questions about quantum mechanics or are curious about the theory of parallel universes, it might be time to dive deeper into these topics. As technology develops, we may be able to unravel these mysteries and further understand the laws governing the universe. The quantum world is infinite, and it keeps the path of scientific exploration endless. If you enjoyed today's discussion, don't forget to like, subscribe, and turn on the notification bell so you won't miss more exciting topics. See you next time as we continue exploring more fascinating scientific mysteries.